We're starting with a polar pi bond, but the big distinguishing feature in this unit is that we now have a leaving group connected to it. Okay? So if we have our nucleophile, that nucleophile can potentially attack. What's the next weakest? We're already there. What's the most likely thing to happen when that nucleophile attacks?
Break the pi bond.
Why should we break the pi bond?
Too many electrons in the carbon.
There's too many electrons on the carbon. Why not just kick out the leaving group?
Because you can't do that all in one mechanistic step.
We're doing a nucleophilic addition and just the elimination of a group.
Another re-resonance for I guess now.
What bond is breaking in each case?
Oh, we're going to pi bond versus
Pi bond versus
sigma.
sigma bond. Which one's stronger?
Sigma.
The sigma bond. It's easier to break the pi bond first. So we go through and we'll break the pi bond. We have evidence for this to exist in the form of the tetrahedral intermediate. So we can prove that that structure does exist. Okay? We now have an intermediate. Okay? That intermediate is unstable. Why is it unstable?
You have a charge.
Charged oxygen. So we'd want to stabilize that. We could potentially stabilize that by having that pick up something like an H+. Okay? But then what we'll have is still that carbon with what is likely to be 3 very electronegative elements connected to it. Okay? Even if it was 2, say the leaving group was an oxygen, that would be an unstable structure because what do we have? Might help if I throw on another hydrogen. What structure would we have?
Carboxylic acid.
We'd have it. Acetal's the right family.
Hemiacetal. No. I'm just throwing
Hem-
out terms.
It's a hydrate because we don't have carbons on there. All we have are the hydrogens.
You're right.
Okay, so the acetal's the right family. That's where I would have said first, but officially it's a hydrate. The hydrate would revert back to the carbonyl in any case. Okay? So we can't really permanently stabilize by adding a hydrogen onto that oxygen. So what are we going to do? We'll shuttle the electrons back down toward the carbon. Okay? At this point, we would exceed the octet yet again, so we have to kick out something. We have to lose some electrons. What electrons do we decide to lose? Lg for leaving group. So yeah, that makes sense. That should leave. That's why we called it a leaving group. Okay? So some of the things that you might have to consider is what is the leaving group in that process. At this point, it's labeled as a leaving group, so it's a little bit more apparent, but it's not always going to be the case. Okay? So this is the core kind of mechanism, if you will. Okay? We're saying core because, and core in kind of quotes, it's not really the core mechanism because we're looking at here probably under specific conditions. Conditions have been implied in this reaction. How do we know conditions have been applied?
Negative oxygen.
The negative oxygen is a tip-off. What else?
Your charged nucleophile.
The charged nucleophile is where I would argue you should start, right? Because the negative oxygen was an intermediate that you, with theory, drew in. So why did you know to draw that negative oxygen? Well, we have the negative nucleophile. How would we get a negative nucleophile? What conditions would we be running under? Basic conditions. Right? So this is showing it under basic conditions. It's the most straightforward of the mechanisms because it's just direct addition and elimination. We don't have to worry a whole lot about secondary reactions. But it does work under acidic conditions, just the mechanism changes a little bit. How does it change? We were to run this under acidic conditions. What would we see as different?
Oh, the oxygen was coordinated.
The nucleophile would be neutral. It would still need those lone pairs, and if it was neutral, as we moved through the mechanism, it would then become positive, and that would be bad, so we would need something that could easily be removed. Bless you. A hydrogen is likely going to be found next to it. What else could we do? change the conditions. So this would now be running neutral conditions.
You could add H plus.
We could add H plus, we could make this acidic conditions. Step one of the mechanism is going to be what? We're going to protonate. Okay. The whole point of protonating is to do what?
Activate the electrophile.
Make the electrophile more electrophilic. By having that positive charge on the oxygen can withdraw electrons from our carbonyl, and we form a very electrophilic carbon. Now what can happen? Now our nucleophile with its hydrogen can come through, and attack. Of course, I ran out of space. Leaving group, OH, nucleophile with the hydrogen and positive charge. Is that showing up on that one? It is. Cool. Now what happens? If we tried to have the lone pair reform, what are we going to kick out? Probably the nucleophile. Why?
Charge.
It's already charged. By kicking it out, we would lose that positive charge. Do we want to kick out the nucleophile?
No.
We want to kick out the leaving group. So what do we need to do to make sure that we don't eject the nucleophile?
Deprotonate the nucleophile.
Take the electrons away from the hydrogen. Have the nucleophile get those electrons back, which means that hydrogen goes floating off the structure, which means that structure is acting as an acid. We would need something remotely basic to pick up that hydrogen. What is remotely basic floating around in solution?
Water.
We could throw water in there. We could throw nucleophile in there. There's a variety of things that could pick up the hydrogen. It's ultimately not that big of a deal. We do have to be a little bit careful, because if we say water and there's not water present, we've got a problem. Okay? So what I would argue is safer is just to say B. B for base. Is it a strong base? How do we know it's not strong? Doesn't have a charge. And we're under acidic conditions. So what I'm trying to do is provide something that is consistent for the mechanism. Now what happens?
Is that supposed to be a leaving group?
That's supposed to be a leaving
Two nucleophiles?
You're right.
I was like, where did that come from?
Now you can reform the pi bond.
Now we can reform the pi bond, kick out the nucleophile.
You kick out the leaving group.
It's Monday. Nucleophile. There's our leaving group. Potentially is a minus charge. We'd still have our oxygen positive now. So now what has to happen?
Deprotonate the oxygen.
Again, we'd have to deprotonate. So we went from a two-step mechanism to, oh my God. Yeah? Okay. We're really still doing those two steps, but we have to account for the presence of the acid in each of those stages to protonate or deprotonate as we move through. Kind of make sense? Okay. So changing acidic or basic can change how our reaction works. We're responsible for understanding that. The same basic characteristic or core characteristic follows, though, that's holding true up in the nice drawn ones. Good? Okay. What is that leaving group kind of is now the crux of the rest of the next two chapters. Okay? So these are the common carbonyls with leaving groups. We've got up at the top what would be referenced as our acyl chlorides, okay, which really is a little over specific. We can call them the acyl halides because it could be a bromine in there, could be an iodine. Typically, you're going to sit between bromine and chlorine. Okay. The next one underneath, These are anhydrides. The next one,
Ether.
not an ether.
Ester.
Those are our esters, followed by
Amine.
amides, followed by okay.
Oxide.
This would be our carboxylates, which was meant to actually be an acid. And we'll address why it didn't show up in the list appropriately in a little bit. Okay, so what is our leaving group in each of those cases? Starting from the top.
The halogen.
Okay, our halogen, followed by
Carboxylate.
the carboxylate, followed by the alkoxide, followed by the amide, followed by horrible, we won't speak of it. Okay, so all of those are our leaving groups. Okay, you'll notice that they are in kind of a stacked order. Does that order have any kind of general effect? Do you notice any patterns in there? Would you look at any of them and be like, that's not going to work? It's not going to happen.
It looks like the best leaving group is at the top, but worst leaving group is at the bottom.
Best leaving group, worst leaving group. Why is the best one the best leaving group?
Chlorine stabilizes the formal charge easily.
Why can chloride stabilize the formal charge? Size and electronegativity. The bottom one, isn't oxygen electronegative?
Yes,
So why is that one bad?
because it's going to leave as 2 minus.
It's going to leave as a double charge, -2. Okay, it started negative. So that's really bad. Okay. The anhydrides. What's the leaving group there? That carboxylate. Why is that oxygen not as good a leaving group as the chlorine? Isn't it? It's not charged, or it's not as charged, right? Why would that oxygen be a decent leaving group?
Resonance.
Look at what happens when it leaves. We would have a negative charge. So really what we're asking you to do is erase the part that does the nucleophilic addition and say, okay, that would be a chloride negative, oxygen negative, nitrogen negative, oxygen -2. Why is that oxygen so good? It's electronegative and there's a resonance stabilization. Yes, David.
Oh, no, it's just
Oh, go back with the resonance, yeah. How about the ester?
gonna,
That's negative oxygen. Why is that one not as good? No resonance. Nitrogen?
less electronegative.
Nitrogen's less electronegative than the oxygen, making it a worse leaving group. Okay? So what we end up doing is switching out our electrophile for one of those functional groups, and then we just throw the nucleophiles at it. What nucleophiles? Well, hydride nucleophiles, carbon nucleophiles, oxygen nucleophiles, nitrogen nucleophiles. You mean all of the nucleophiles we studied in the last 2 chapters? Yes. The exact same reagents that you saw in chapters 17 and 18 come back again, now with this structure. Okay? How does that change the reaction? Well, in 17 and 18, did we have a leaving group? No. Here we do. That's the crux of everything. Okay, so really all we're doing is repeating chapter 17 and 18. You wanted more practice, right? Here you go.
Thank you.
Yeah, because it's my fault that you get practice. Okay, so we already addressed the could they be changed, sequencing of the timing on that. We had the top and the bottom, best at the top, right? And worst. What would that mean for our mechanism? What is that going to change about our reaction?
it off.
It might be easier to take it off is entirely different than less mechanistic steps. Okay? So it might be easier to take off. I completely agree with that. That's a decent sentiment to talk about, and that's where we're getting at. Okay? Not less mechanistic steps. Okay? If we're talking about the mechanistic steps easier to take off, you're saying that that leaving group is stable. It is easier to break that bond. Right? I have to form that first, don't I? If I don't form it, I don't care what the leaving group is. Right? This goes back to substitution, looking at those reactions. We'll get people saying, oh, a primary carbocation is super, super fast, so SN1 loves primary carbocations. No, SN1 don't react with primary substrates. Yes, if I form the carbocation, it would react very, very, very fast. Do I form the primary carbocation? No. Okay? So we have to be careful at using our judgment appropriately at the appropriate steps. That very first step is probably our rate determining step. Why? We're going from relatively stable to relatively unstable. The second step is probably going to happen very fast because we're going from relatively unstable to relatively stable. So while looking at the leaving group is a common answer for explaining the reactivity here, it doesn't quite fully play out. Okay? You're looking at very subtle nuances in that explanation, and the majority of the time you'll be okay. Okay? But officially that doesn't work. What do you have, David?
I was going to say you're going to have to figure out your nucleophile, because if you have a...
Nope, we're not going to worry about the nucleophile at all either, because if you're saying you can change the nucleophile, well then that changes all of these accordingly. We have to react them under the exact same conditions to make a fair comparison between those substrates.
Then is it, you're looking at conditions?
Again, the conditions would be the same. We have to look within these structures to decide how these structures are affecting the overall reaction.
You're just slowing it down. Make it worse, right?
What is slowing it down?
It's less energetically preferred. So
Which one is less energetically preferred?
the lowest one would be the O2 minus leaving group.
Okay.
To have your highest energy products. So
Highest energy product. So you're saying that this product, that red one, will be up here, and this purple one will be over here, yeah?
yes.
So what you are again addressing is exactly what Alex was addressing. The second step. I don't care about the second step yet. I need to achieve that intermediate. What about those structures allow me to achieve that intermediate faster? Looking at the speed of the second step doesn't help.
Do you have to look at your electrophile?
We have to evaluate the electrophile, yes. So let's compare. Let's get rid of those structures in the middle and simplify this.
The top is more reactive.
Why is the top more electrophilic?
Induction.
Okay. There's an inductive effect here, making that positive more positive than the positive down here. The bottom one actually has resonance to do what to the positive? Stabilize it. So if I'm going to add these two starting materials onto my energy diagram, where would I place them? Where would I place the red one in comparison to the purple one?
Higher. Or sorry, lower.
The red one being more stable should be lower in energy. Where should the purple one be?
Higher.
Higher in energy. Why does this help us out? Which one of these is going to go faster?
The one that's already higher energy, because you have less activation energy.
We have less activation energy in that very first step. It's looking at the strength of the electrophile. Okay? Yes, the leaving group contributes to that, but that's not the answer. The leaving group is the second half of this. Does that make sense? So what we're saying is that each of those structures changes their energies. So their electrophilic characteristics change. The worst one I drew where?
At the bottom
At the bottom. Where's its energy on the energy diagram?
At the bottom.
The bottom. It's the lowest energy, making it the most stable. The most reactive one, our acyl chloride, we drew at the top. Where is it on the energy diagram? Higher up. Okay? So that sequencing that was drawn in initially is reflected in the energy diagram. That's why they were drawn in that fashion. Okay? Questions about that? Okay. So we could go through and look at an energy diagram and evaluate your reactants, your intermediates, and your products. For the most part, the intermediate is all roughly the same energy. Okay? It's the same now, neutral nucleophile attacked. The leaving group hasn't left. It's neutral. The only thing that's driving the energy of that intermediate is that negative oxygen. Okay? So our intermediate energy is roughly the same for all of these, and it's going to be very, very high. Okay? What happens with the reactant energies? And of course, this is stepped, so there goes my purple thing. If we compared the ester to the acyl chloride, well, the acyl chloride is more electrophilic, meaning the energy necessary to make it to the intermediate is much, much lower, so it'll react faster. It's also going to get reflected out the other end, right? Because if we look at the leaving group for the acyl chloride, that leaving group is
Very stable.
very, very stable, which means the product energy for that one is very low. What is it for the ester?
Fairly high.
Okay. Relatively the same as we started, and if we look at it in this case. Okay. Kind of, sort of? Yes, that doesn't look pretty, and the textbook does a much nicer picture. So each of the starting electrophiles is really just changing where its energy starts at. If it starts really high, that reaction is going to go very fast. Okay? If it starts really low, that reaction is going to go very slow. We can hand-wavy cheat by looking at the ability of the leaving groups, and for the most part, that works out nicely. Okay? But it's not the strict answer behind it. Make sense? Was there a hand?
Yeah, if they're at the same level for the ester, isn't that in equilibrium? Because you've got the activation area, you can go one way.
So one of the complications we're going to encounter is some of these are actually synthetically useful. Some of them aren't. Right? For instance, if we go I'm going to step all the way down to that bottom one, would that be a synthetically useful electrophile? Would I expect that one to react?
No.
No. And because it doesn't react, I don't use that one as a reagent. Okay? So ultimately what we're talking about is how those things stack and how we can potentially get them to interact and interconvert. Okay? And one of the big challenges here is when we shift between this, okay, and we saw this one already, what if we had a nucleophile that was bromide and our leaving group was OAC? So we jump to the product, bromide, leaving group was OAC. What is OAC? Acetate, right? And we looked at that reaction. Is that reaction likely to occur?
Probably not.
Right, probably not. Why not? Which of those is the more stable structure? Bromide, which would suggest which way does our reaction go? Towards the reactants. Okay? So if we look at our diagram, if we start at an acyl chloride, we can work our way down. Going up, not so easy. Right? And so what we're going to see in, I think, 2 slides is this ladder effect. Right? And what we're talking about doing is how we can oscillate on the individual rungs of the ladder. If we're at the acyl chlorides or acyl bromides up at the top, we can do anything. It's like a reading rainbow. Some people are shaking their heads. That's okay. But if we start at the bottom, it becomes very difficult to move up. Very difficult to move up actually could be a good thing. Because if it's difficult to move up, how many reagents are there? 1. Right? So it can help simplify your memorization process. If you can organize where they are as far as reactivities, you know that if you're at the top, you can go anywhere. If you're at the bottom, you have to only go through very particular paths to move up. Why would you move up? Because you want it to react to make one of the bottom things. Okay? So, this can be done through rates. Okay? So if you remember 152, we can look at rates of reaction. Okay? In this case, they picked water. So we're reacting each of these electrophiles with water. Okay? That's kind of a weird statement to say, react with water. So we can instead refer to it by the Greek or Latin.
Hydrolysis.
Hydro for water, lysis for cutting. We're literally using water to cut apart the electrophile. Right? So if we look at the rates, you see for your acyl chlorides, your rates are very, 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 very fast. Right? For your other substrates, those rates end up going too slow to actually do anything useful. Okay? We address that by looking at the energy diagram. It's all just a question of that activation barrier. This is just the mathematics behind it, if you wanted that. Sorry, yeah?
That last one, and just a dash, says it doesn't happen because that's more stable than the OH.
Yep. You'll also notice that this one's kind of nice, because what else do we see in this? Are these all leaving group substrates? All of these electrophiles have leaving groups. No. Which ones don't have leaving groups?
The ones that don't have a leaving group.
So we could say the ones with dashes, right? There's a dash, there's a dash. Well, that one made sense. O-2, that's a horrible leaving group. That would never happen. What's the other ones?
Carbon or leaving groups or H.
Carbon leaving groups or hydrogen leaving groups,
Yeah.
also known as aldehydes and ketones, also known as chapter 17 and 18. This is useful to incorporate into this diagram. Remember all the reactions we talked about with aldehydes and ketones and how some reactions reacted favorably with one but not with another? Right? They're on this sequence of rates. Aldehydes and ketones react more than acids and esters. Why? Why is their electrophilic character better than acids and esters?
Because acids and esters don't have the it's better than acid because if you split that off.
Split that off is immediately saying leaving group, and I'm going to say no.
Okay.
Remember, we're talking about the electrophilic character. Why is the electrophilic character of our aldehydes and ketones better than that of the acids and esters?
The acids and esters have resonance, stabilizing the positive on the carbon.
Those have a resonance effect.
Yeah.
The aldehydes and ketones don't have that resonance effect. So if we were going to place them in this diagram, they need to be higher in energy than our acids and our esters. Should they be as high as the anhydride? Doesn't the anhydride have resonance? Aren't there lone pair electrons that could be donated to stabilize that electrophilic carbon?
But then you make the other one worse.
Yeah.
Now the other half is worse. So yes, there's a resonance contribution there, but that resonance contribution really only goes to explain that the leaving group can leave. Okay? When we jump up to the chlorides are now so electronegative and other things that we don't need to address, they don't have that resonance, and it's just that inductive withdrawing effect as well. Okay? It is important to fit the aldehydes and ketones in there because you will see questions that are asking you to relate their reactivities to the overall systems. Okay? If we drop it into an energy diagram, see, textbook did a much prettier job of this. We're looking at the stability of those electrophiles. The more stable they become, the larger the activation barrier for that reaction. Okay, so that they're just looking at that first step. That's all we're talking about. Make sense? Okay. Stability of the leaving group. This is our cheat. Okay. Evaluate your leaving group in comparison to your nucleophile. If your leaving group is more stable than your nucleophile, then what does that mean?
Reaction is unlikely to happen?
If the leaving group is more stable than the nucleophile.
Oh, wait, it's likely to happen.
Likely to happen. Make products. What if your nucleophile was more stable than the leaving group?
Makes reactions.
We could say makes reactants, or we could say no reaction. Okay, that reaction is unlikely to go. Now remember, that's our cheat through this, but it works pretty well. That'll cover our bases for most of our reactions. Okay? David? You done? I thought you had a question. Okay. OChem is pain, princess. Summary of inner conversions. Okay, so if we go through, here's our ranking, our acid chloride at the top, our anhydrides, our esters, the amides, and then the carboxylate. Okay, what this is showing is that ladder and how we can move through it. Note that if we start at the acid chloride, we can go pretty much anywhere down. Okay? If we start at the anhydride, we can only go certain spaces down. To make it up to the acid chloride, where do we have to start?
Acid.
We have to start at the acid. Okay? So that means if I'm at the anhydride, I have to drop down to the acid to then go up. Interestingly, look where the amide is. The amide is underneath the ester. Why does that make sense?
Because nitrogen has resonance into the carbon.
So does the oxygen. Why is the amide less than the ester? Electronegativity. The nitrogen is less electronegative than the oxygen.
More comfortable.
Okay. So it's more willing to share those electrons, making that electrophile more stable. Note, from there, we can go up. That's a bit interesting. I would argue that's kind of an exception to this. The amide can go upwards. You'll notice the carboxylate can go upwards to the acid. I would argue that is not an exception. Why is that one not an exception? What am I adding? What kind of acid? Usually a strong acid. Okay? The carboxylate to the carboxylic acid, those conversions, you're adding in stupidly strong reagents to force that chemistry. Those don't really fit within the category as going up and down. Okay? Questions? Going from the acid to our acyl chloride, how do we do it? Add SOCl2. You should be able to do better than that. We barely talked about this in Unit 1. In Unit 1, we talked about this. You should know that reagent. Tosyl's not a bad idea. We did drop it in that context. But the tosyl was the benzene with the methyl. Okay, there's no benzene here. That reagent is thionyl chloride. What did we use it for back in Unit 1? It was a substitution. It was to convert our OHs into better leaving groups, to convert them into the chlorides. Okay? It was talked about primarily in the context of alcohols into alkyl halides, because we wanted the alcohol, or wanted to get rid of that alcohol reactivity, because the alcohol could do anything. If we converted it to the alkyl halide, we limited the amount of reactions, which was nice. Right? But in that context, I also said that the thionyl chloride was so reactive that it will convert any OH into a chloride, including an OH found next to a carbonyl, i.e. the carboxylic acid. That's where our thionyl chloride comes in, and that's where its primary reactivity is valuable. Right? It's getting us to the top of this ladder. Why do we want to be at the top of the ladder?
So we can come down?
So we can come to any one of those levels below it. Okay? That becomes synthetically very, very useful. Okay? If you look at most of the arrows in there, they're unidirectional. Okay? Again, it's that ladder aspect. We can only work our way down, not up. Okay? It's probably better to call it a waterfall, okay, than a ladder, right?
Yeah.
I was going to start trying to horribly sing to that too. So let's move to the exceptions. Okay? We talked about, the amide. And we said the amide moving up to the carboxylic acid was an exception. Okay? Because that's a little weird. The amide is more stable. Why would we be allowed to make that transition upwards? Okay, well, to figure that out, it's helpful to look at a mechanism. Right? This one's going to be an easier mechanism to evaluate because we're running it under basic conditions. We ran under acidic conditions. That's where we get all the protonations and deprotonations. Here, for the most part, it's kind of just a direct reaction. So, how's it going to start? Okay, we've got a suggestion for the OH to attack. Okay, so we've got OH minus. Any other suggestions? Okay, my suggestion. You have two O minuses. Why'd you pick the red one, not the purple one?
Sterics.
Cool. The T-but or the T-bu is for T-butyl. That is sterically huge. That negative oxygen is there as our base. Right? It's not there to actually act as a nucleophile. So we are looking at the hydroxide acting as our nucleophile. Okay? If it's a nucleophile, where is it going to attack?
Carbonyl carbon.
It'll attack our carbonyl carbon. The next step is
break the pi bond.
break the pi bond. Okay? The result, I'm not going to draw out that phenyl ring, so I'm going to write it as pH. Okay? This is a phenyl. Of course, Cardi had to pick something really freaking huge. Yeah? This is where I would argue we have three very electronegative elements all connected to the oxygen. That is not such a great thing. So that carbon's now going to get a little bit irritated and try and draw electrons back. Where's the most likely place it could get those electrons from?
The nitrogen.
Nitrogen's not a bad idea, but then nitrogen's going to become positive, and there's no way for it to fix that positive charge. Right? Because it would then have to remove electrons from the carbons. Right? It could get them from the hydroxide. If it pulled the electrons from the hydroxide, what happens? We go backwards. So is it in equilibrium? Yes. Where else could it get electrons from?
The other oxygen, pull those down into a pi bond.
The other oxygen, remember, reform our pi bond. Okay. What's the result?
You can see the octet there.
We would now exceed the octet, so we would need to kick out a leaving group. What's our leaving group? Okay. The nitrogen's our best bet here. Okay? Remember, if we got our reaction shows that it needs to leave, right? Okay? So we could have it leave. What do we get? Okay. Were you guys just leaving the nitrogen for the last just for the heck of it, or did you really not want to kick out the nitrogen? Because there were three options, and you guys did save the nitrogen, the one we wanted, for the very last.
To be honest, I didn't even think before I thought.
Fair enough. So we got one answer. Rob, you suggested the OH. Why'd you pick the OH before the nitrogen? There doesn't have to be a reason.
I would be in favor of saying we don't see nitrogen as a negative formal charge very often.
Okay? But if the oxygen, and I just realized I did a horrible job with that arrow that I had up there. Sorry. If that oxygen took the electrons, we'd be having a negative oxygen as opposed to...
For electronegativity.
So if we look at electronegativity, the oxygen should hold that charge better than the nitrogen. That reaction right here, not a good reaction. We're ending with a negative oxygen when we started with a negative nitrogen when we started with a negative oxygen. Which one's more stable?
Negative nitrogen in this case?
Negative oxygen,
In this case.
because it's more electronegative. Okay? And so by saying in this case, you're saying, but this reaction happens. You're right, this reaction happens, but that step sucks. That step is actually not likely to happen. We would rather have the negative charge on the oxygen. That, as an equilibrium, heavily favors the reactants. This is why we can't go up in the ladder. We're going up to a higher energy state. We're not allowed to do that. That's a bad mechanistic step. And yet somehow it's happening. Okay? And the question becomes, why is it happening? Okay? You're answering the question, or you got a new question?
No, I was wondering, does it happen at all?
Yes, it does happen at all because we get a very high yield. If we take a look at our product, 96% yield.
This step.
This
not
step,
that.
yes.
That one happened?
Yep.
You created an acid in a basic solution.
We have a carboxylic acid in the presence of a strong base. What is the very next step that happens almost instantaneously?
Acid-base
Use the
neutralization.
hydrogen from the acid.
We almost immediately get an acid-base step. We're forming not a strong acid, but we're forming a relatively more acidic acid in a very basic environment. That's not so great. So the base immediately comes along, removes that hydrogen. It happens to be the most available thing. If we go through and look at that reaction, we're now forming a negative oxygen and a neutral nitrogen. Is that reaction likely to revert? No, that reaction very heavily favors the products. So while the previous step may happen very, very slowly, as soon as it happens, we immediately revert to a negative oxygen. And that step happens exceptionally fast. That step is also irreversible. It's that incredibly fast acid-base step that actually facilitates this reaction. Okay? It's a secondary aspect of our nucleophilic addition elimination reaction. Is that our product, though?
No.
No.
This is step two.
That's why there's a step 2. We have to do a step 2 because we formed a strong base that deprotonated our product. We then have to place that hydrogen back on the structure. Kind of, sort of? Okay. So that's how we're moving up in the ladder. Our intermediate structures that should not form by all rights react so quickly once they are formed that the equilibrium is allowed to kind of constantly siphon off that small amount of product to make our final product.
I was wondering, like, because I was gonna go back and say, do we basically the OH run the atoms from the H bond to the oxygen, form the double bond that way, kick out the limit? That's what I
So
was- as an option.
there was a suggestion, if we erase arrows back here, we'll go ahead and show it in blue. I believe what you want to say is have these electrons from that hydrogen go to that oxygen.
No, into the bond to the oxygen-carbon bond. So roughly, I'm hand waving the fact that they come onto the oxygen kicks the pair down, and then the nitrogen extends out to the.
You're effectively forming a double negative charge in that structure. So, no. What you would have to do is then say that those electrons somehow picked up the
That's
hydrogen.
what I was like a cycle.
And why would that be unlikely?
Intramolecular reaction. You're only making
Intramolecular isn't necessarily bad, but having a four-membered intramolecular reaction, 1, 2, 3, 4,
Okay.
is bad. Okay? So the mechanism that we gave initially is going to be our best bet.
Okay.
Okay? We can see this in an energy diagram that Cardi puts together for us. We've got the initial nucleophilic addition followed by the nucleophilic elimination. Notice again, the carboxylic acid is higher in energy than the amine. Okay? Because of that difference in energy, we would expect that reaction to not work. Okay? There's this giant white space because there's more. We do the acid-base reaction that deprotonates. We now form the much more stable carboxylate, lower in energy than our amide. That's what's allowing that reaction to actually continue through. The next step is in the acid-base, which becomes irreversible because we're throwing in a strong acid.
Didn't you make the carboxylate in step 2 and then adding acid would reprotonate it into a.
It would protonate it. We haven't made the carboxylate. If you look at the mechanism, the carboxylate only shows up here. It's the end of step 1. Adding H plus is step 2, which isn't on the energy diagram because they're trying to show that as a separate issue.
Okay.
Right? So if we move through and we look at our acid derivatives, right, the things with the carbonyl in the leaving group. Carbonyl in the leaving group, we've got our amide. Carbonyl in the leaving group, we've got the acid. Carbonyl in the leaving group, which is boxed now in purple, is our carboxylate.
I had thought that the bottom step was the end of the reaction.
Nope.
After the acid, and that was
Nope.
Okay.
Yeah. And if we go back to the referencing on the energies, we have amide, acid, amide, and carboxylate, which is exactly how it was organized off the chart. Kind of, sort of? Okay. So that one's kind of neat because of that reactivity. It's that same reactivity with the amide that was also already taken advantage of on that quiz that we took last week. Right? It was a named reaction. What was that named reaction? It was talking about the amides.
Wolf-Kishner?
Nope. Wolf-Kitchener's a reduction, not dealing with the acid chlorides or the acid halides. Okay. It's our Gabriel synthesis, which we'll see here in just a second. Just because I know some people look at slides, this next slide, if you're looking at it, don't worry about it. Right? That one's wrong. Last fall, there was a big issue that caused problems. There's our Gabriel synthesis. Okay? We've got our hydroxide with the amide, okay, which looks very much like what we just went through, except this one, that hydroxide isn't acting as a nucleophile. Okay? It's going to act as a base in this case To do what?
Take the hydrogen from the nitrogen.
To remove the hydrogen from the nitrogen. Why is that hydrogen acidic? There's a large electronegativity and inductive effect here. Very minor aspects as resonance. Okay? You don't need to stress about that, but we're looking at an acid-base reaction. That acid-base reaction creates, of course, we got to draw the whole stupid ring. That very strong nucleophile, which we can then react with
The alcohol.
wasn't an alcohol, an alkyl halide in a substitution reaction. Is it ringing any bells? Vaguely, yeah. Okay. Once we've done the substitution reaction, we can then follow it up with a second round of hydroxide. Okay. That nitrogen now would no longer have any more acidic hydrogens on it. We would have our alkyl halide connected to it. So now what does the hydroxide do? Now it acts as a nucleophile, attacks the carbonyl. Which carbonyl? Either or, sort of. Either or at once. Once it's done it once, can then do it twice to the other one. Right? And the end result is that we end up kicking out the amine, and we get a primary amine. Okay? We get a single nitrogen connected to our alkyl or carbon chain. We said that was nice because nitrogen as a nucleophile is super nucleophilic. The Gabriel synthesis limits that nucleophilicity because it keeps it bonded or tied up into the resonance with those carbonyls. Okay? So we can get primary amines with relatively high yields and, more importantly, relatively high purities. Okay? So it's a big step above doing our standard substitution that we talked about again back in chapter 10, okay, which is to nitrogen and alkyl halide. Notice the yields come out about the same. It's the purity that's the difference. Okay? With the standard nitrogen nucleophile, it's virtually impossible to remove those other impurities. With the Gabriel synthesis, your impurity is either starting material or a carboxylate salt that's water soluble. Okay? So it allows for a much cleaner separation. So that's kind of neat. Questions about that one? Okay. Haloform. This should look familiar again. Okay. What happened under these conditions? What did we get?
You formed a carboxylic acid.
Okay. And so this is where we need to be careful. We're seeing some keywords and you're jumping on the memorization of what happened. Look at the reaction.
Halophore, you put both bromines where the oxygen was?
Okay. No. What's the reactivity of Br2? It's an electrophile. It's coming in as a Br positive primarily. If we look at the the carbonyl carbon, what is that charge? Positive. H plus? Positive. Okay. Where's our reactivity? What's the most reactive thing there?
Oxygen. H plus.
H plus is a strong acid. You should immediately be jumping all over the H plus and trying to neutralize its reactivity.
Hit it with the oxygen.
We need a source of electrons. Where's that source of electrons? The oxygen. What happens? Whoops. Whoa. You just delete the whole oxygen. we'd have a whole positive oxygen. Does oxygen want to be positive? Nope. So what can it do? It could pull the electrons. Officially, we could make that reversible. But it could steal electrons. We'd be drawing resonance. In that resonance, what are we showing? A positive carbon. So we took one positive and we made another positive. But at least we got rid of a positive. Right? That's a good thing. So now what happens?
One bromine's positive, one's negative.
The hydrogen.
One bromine is officially negative, but it only becomes negative once the other positive bromine has been removed. So therein lies the problem. We can't get access to a negative bromine if we don't first use the positive bromine. What do we need? We need electrons, right? We need to find some place for electrons. Okay? I currently see 1, 2, 3, 4, 5, 6, 7. I see 8 places for electrons in that red structure. What are the 8 places I'm referencing? So I heard a reference to hydrogens. There's 12 hydrogens.
You need to look at alpha hydrogens.
Okay. Answer the question that I asked first. There are 8 places with electrons in that structure. Where are those 8 places? The bonds. There are 8 bonds shown. Every single bond is a source of electrons. Okay? If I tried to pull electrons from one of those bonds, I end up forming more unstable structures than I'm starting with. Okay? And for those of you being like, I wonder what that would look like. Okay? You should already know, because I asked you to do that in the past. I asked you to chase down these horribly wrong paths to see what would happen. So let's take these electrons and give them to that carbon. What would the result be? Okay. Put a lone pair of electrons on that guy now.
It's going to be negative.
Okay, will it be negative?
No.
Why not?
You use those electrons to stabilize the positive, it should be neutral.
Okay.
It also doesn't have a hydrogen in it. That was an implied
It
hydrogen.
doesn't have an implied hydrogen.
It's not octet though.
It's not octet. Okay. That carbon only has 6 electrons around it. Green was an awful color, I apologize. That carbon only has 6 electrons around it. So that is screaming as a bad move. Why else was it bad? Someone else suggested the potentially more obvious aspect.
Yep, positive carbon.
That carbon is now positive, and we now have a primary carbocation as opposed to, depending on how you want to evaluate that one, I would call it tertiary. Okay? Or secondary plus resonance. That was a bad move. Were there electrons? Yes. Could you do it? Yes. Is it energetically favorable? Hell no.
Haven't you made that also black octet? Because
To have a carbocation, you have to lack octet.
yeah.
Okay? So where else can I find electrons? Okay? And by referencing the bonds there, what I'm trying to get you to do is to think that there are electrons in bonds. And it's not a think. No, that's the whole point of a line, is to represent the electrons. Okay? One of the most commonly missed source of electrons is bonds. Okay? But we need to take it a step further. It's in a bond
Well, there's the bromine
that
bond.
isn't shown. Where's that bond?
Or the electrons, the bond between the
The implied hydrogens. those electrons can be removed. Forming what structure? An enol. What are we looking at? A keto-enol tautomer. That is critical to evaluate this. Was a hydrogen suggested? The hydrogen that I heard reference to was the hydrogen that was already on the oxygen, or a hydrogen that was referenced after I wanted you to push into the details of the reaction. If you don't want me to push into details of reactions, that's cool. Start feeding me answers that take us forwards. That's how it works. Okay? What is special about the enol? Those electrons can come back down, making that alpha carbon negative, a nucleophile. So those electrons can now come out and attack our positive bromine. What's the result?
Would you get a 3-membered ring?
Yeah, you get that 3-membered intermediate structure.
Okay? So you're saying putting a 3-membered ring here?
Yes.
Okay?
And never mind.
What do your arrows show? Okay? I know exactly why you want to form a 3-membered ring. Because you're like, it's an alkene reacting with bromine. We should form the bromonium ion. That in and of itself is a pretty cool leap of logic and thought process and fantastic. Except what you've done is unfortunately memorized a fact and are misapplying it. This is not an alkene. This is an enol. Okay? So you can't just start jumping on those things. Look at what the arrows show. The oxygen electrons come down to form a pi bond. Okay? The alkene electrons sit on that carbon. Those then react with the bromine. This is not a standard alkene. This is a polarized alkene, which is why it's reacting out in this fashion. Which means the result that we get is just the bromine. Whoops, that's an eraser. Which is just the bromine connected with Br minus then floating around. Yes?
You draw arrows taking away electrons from the hydrogen up there. Is that an error, or should that still be on there right now?
Should still be there. What happens now?
Bromine negative attacks the the partially positive carbon, pushing those electrons. Because like carbon is even more partially positive than normal because that carbon, the oxygen really doesn't want to be positive.
So for the record, we've discussed this reaction. What do you guys think?
Looks pretty gnarly. You've got 2 electronegative.
We have a tetrahedral carbon with 2 electronegative elements connected to it.
You've got
That's begging as a tetrahedral intermediate to do what?
One of them out.
Kick one of them out. How could you stabilize that positive oxygen? Deprotonate it. Yeah, that's probably the easiest answer. Okay. What happens if we deprotonate that? Okay, cool. Again, I like the idea. You've got some of the facts of the memorization down, which is good. So we're churning through those wheels. Haloform, we do it again.
All I know is
When do we do it again? When we're under basic conditions. What happens if we're under acidic conditions? What needs to happen?
Become a better acid.
We would need to protonate that with acid. Blue structure versus black. There's the black circle. There's our blue circle. Which one's the stronger acid? Or sorry, base?
the black one
The black one? Why?
doesn't have bromine on it.
It doesn't have the bromine on it. So what are you saying this bromine is doing in the blue structure? Pulling the electrons into the structure. As the electrons come into the structure, what happens to the base strength? It decreases, which means the blue structure will not react with acid, which means it does not get activated, which means
Kills reactivity.
reaction stops right there. We've done a single substitution. Okay. Haloform, you're right. You're triggering on terms, but then you're just jumping on a rote memorization of those terms. Look at your reactions. Under acidic conditions, we stop there. How do I do the haloform? I need basic conditions. So, what should we do? Make it basic. How does that change the reaction?
Now you have acidic hydrogens.
The alpha hydrogens are still present. Because that is a strong base, it can directly remove those alpha hydrogens, converting it into the effectively, or better, sorry, not enol, but enolate because it's charged. We're still doing the keto-enol tautomerization. You mean I can do it in one step as opposed to two? Or one step as opposed to however I had 3, 4 steps? Remember, acid conditions change the mechanism around. We have to be cognizant of that. As soon as we have the enolate, now what can happen? We again have that nucleophilic carbon that can come out and attack our bromine. And we can put the bromine on. Now what can happen?
You have even more acidic hydrogens.
That red structure has more acidic hydrogens than our blue structure. Why?
Induction.
We have an inductive effect of that bromine, withdrawing the electrons that can pull the electrons away, and this reaction runs away on itself to do a full substitution. Okay? All of the alpha hydrogens get substituted out for bromines. I know that looks like a double bond. That's not a double bond. Does this one fit the haloform test?
Shouldn't the oxygen not be there to be helpful?
To do the haloform, I need to keep going. I need to do something else. The haloform, if we're doing bromine, is that structure. That is haloform. In that case, it's bromoform. I have 3 bromines connected to a carbon.
No, this is not fit.
This one doesn't fit that category. This one, as a substrate, does not react in the haloform condition. What do we need to make it a haloform condition?
Methyl ketone.
We need a methyl ketone. Once we have a methyl ketone and our basic conditions, this reaction will go through with 3 substitutions. We now have a carbon with 3 very electronegative elements connected to it. Is that carbon happy? So what is it going to do? Okay, it's going to leave by taking the electrons away. The resulting structure could look something like this. And it doesn't, and I'll explain why it doesn't in a second. Okay. Why does it not just leave?
Leaves as a negative carbon.
Okay. Is a negative carbon particularly stable? No. Okay, but we've had negative hydroxides that left. Yeah, this is carbon, 3 electronegative elements. Why else would it not just leave?
Why didn't it just go back?
Why would it go back? I think you're getting at the right idea. There's a carbocation. That's not particularly stable, right? How could we help stabilize the formation of that carbocation? Okay. If we show this in a slightly different fashion, we have a carbonyl and we have a leaving group, right? And we have like a nucleophile in the case of hydroxide. If our hydroxide comes in, we no longer have that carbocation. We still have a negative carbon. Is that good?
And then steal it from the acid.
Kind of like what?
Carboxylic acid base.
Kind of like the carboxylic acid base reaction that we just ran with the amide. There's our haloform. Okay. We would have a negative oxygen. Is that good? No. So depending on what we're trying to do with this reaction, if we're trying to make a carboxylic acid, we can now add H+. Typically, this reaction is not used to make carboxylic acids. It's used to do what?
Make the precipitate.
Make the precipitate. Why do I care about this precipitate?
Negatively charged carbon.
No, I don't form a negatively charged carbon with any appreciable rate because it immediately reacts. What's the deal about making this precipitate?
You can use it to test for ketones or alcohols.
I can use it to tell me that I started with a methyl ketone, that I had a carbon with 3 alpha or 3 acidic hydrogens. Why were they acidic? They were alpha to a carbonyl. And they're acidic because I can go through the keto-enol tautomerization. All of that chemistry stacks. Okay? So slow down a little bit when you go through and look at these. Okay? It's not just memorizing terms. The ACS is going to ream you on that. It's okay to hold the term, but then look at the chemistry that's present. Okay? We just walked through that mechanism, so we'll leave that alone. We'll pick up there on Wednesday with our hydride nucleophiles. We already talked about sodium borohydride and lithium aluminum hydride. We're going to see them go through with our acid derivatives. Okay?